Hello everyone. In the previous session we have discussed some of the properties of outer measure, that is monotonicity property of M star, and countable subadditivity, and the third one is outer measure of an interval is equal to length of an interval. So these are the properties we have discussed in the previous session. So let's move further now. So using this property, let's solve one corollary and one problem. Corollary statement says that the set 0, 1 is uncountable. We have to prove that the set is uncountable. In order to prove this corollary statement, let us assume in a contradiction way. So contradiction for this is assume or let 0, 1 is countable. So in one of the theorem we have seen that outer measure of countable set is 0. Using that I can say that outer measure of this 0, 1 interval is 0. Okay, but from length of an interval concept, length of this interval is equal to 1. Here outer measure of an interval is not equal to length of an interval, but from properties we know that outer measure of an interval is equal to length of an interval. So the assumption is wrong. Therefore this is the contradiction. This is contradiction to the fact that zero, 1 is countable. So I can conclude that therefore 0, 1 is uncountable. The next problem is, if outer measure of a set A is 0, then I have to prove that outer measure of A union B is equal to outer measure of B. In particular, if B is a subset of A, then outer measure of B is equal to 0. So from countable subadditivity, I can write M star of A union B will be less than or equal to M star of A plus M star of B. This is by countable subadditivity. Okay. So from given thing we have M star of A is equal to 0. So this becomes M star of A union B will be less than or equal to M star of B. So this is inequality 1. If I prove this inequality in a reverse way, then I can say that M star of A union B is equal to M star of B. So using set theory concept, I can write B is a subset of A union B. Okay. So from monotonicity of M star, I can write M star of B will be less than or equal to M star of A union B. This is from monotonicity of M star. What monotonicity property says? If A is a subset of B, then M star of A will be less than or equal to M star of B. So that condition I am using here. So from 1 and 2, inequality 1 and 2, I can say that m star of A union B is equal to m star of B. The another part of the problem says that if B is a subset of A, then m star of B is equal to 0. So they have given B is a subset of A. Using monotonicity property of m star, I can write this as m star of B will be less than or equal to m star of A. Given thing is m star of A is equal to 0. So m star of B will be less than or equal to 0. Since outer measure cannot be negative, this will be m star of B is greater than or equal to 0. So from these two I can conclude that m star of B is equal to 0. So initially we were having this situation, length function, here set of all intervals and this is power set of R, that we have denoted as m star. We are generalizing m to L, but here in power set of R only two conditions are satisfying. The another one condition is not satisfying, which is that is countable additive. So for that, Henry introduced an intermediate set such that this length is set of all interval is subset of this set, and this set is subset of power set of R. This is what we called as M, that is Lebesgue measure. And here what we have told that all three properties are satisfied here, isn't it? So countable additive means m star of union I is equal to 1 to infinity EI is equal to summation I is equal to 1 to infinity m star of EI. Here EIs are disjoint. That means EI intersection EJ should be equal to null set. So in fact for m star we had this property, that is m star of union I is equal to 1 to infinity EI, which is less than or equal to summation I is equal to 1 to infinity m star of EI. This property is nothing but countable subadditive. So here EIs need not to be disjoint. So if we consider power set of R, this countable additive is not even finite additive. That means m star of union I is equal to 1 to n EI is equal to summation I is equal to 1 to n m star of EI. So this cannot be, the finite additive property also will not be satisfied in the case of power set of R. Okay, so in order to show that all the conditions satisfy in M, let us first define what is M. How we can define M? M is nothing but Lebesgue measurable set or set of subsets of R, and that subsets of R we call it as Lebesgue measurable subsets of R. So now this is the situation. This is set of all intervals. L is the function, that is length is the function. This is a subset of this intermediate set, and this intermediate set is subset for all power set of R. This intermediate set is nothing but set of subsets of R, and we call it as Lebesgue measurable subsets of R. I will denote it as LMS. In this intermediate set, what we were telling from the beginning itself, all the three conditions are satisfied. Which are those conditions? One is translation invariance, that is m of e plus y is equal to m of e, or m star of e plus y is equal to m star of e, and countable additive, and one more is m star of e is equal to length of e. So these three conditions will satisfy in this intermediate set, that is in Lebesgue measurable set. In order to check all these conditions, first let us define what is Lebesgue measurable set, or how we can define Lebesgue measurable set. So now I will consider one subset, a subset E of R. So if I say E is Lebesgue measurable set, then this must satisfy this condition: m star of A is equal to m star of A intersection E plus m star of A intersection E complement for all A subset of R. This is the condition. If this condition is satisfied, then you can say E is a Lebesgue measurable set. I repeat, any subset A, any subset E of R is said to be measurable or Lebesgue measurable set if m star of A is equal to m star of A intersection E plus m star of A intersection E complement for all A is a subset of R. So what you have to do here, you have to select your set E, which you have to check whether it is a Lebesgue measurable set or not. So basically you have to select a set and then you have to choose all the subsets of R. This A is any subset of R. So A will be any subset of R. Okay, you have to check for every subset of R. So you should get this thing. Suppose this is your set E. This is your set E and this is another set A. Then this portion will be your A intersection E and this section will be A intersection E complement. Okay. So taking any set A of R, m star of A is equal to m star of A intersection E plus m star of A intersection E complement. So basically your set E should divide any subset A of R such that the total outer measure of that set, is equal to sum of outer measure of two parts in which E is divided. So E is divided into two parts. No, the sum of those two parts will be equal to total measure of outer measure of that particular set. So this is the definition for when do we say that a set is Lebesgue measurable set. So there is a small simplification, that is this is my Lebesgue measure. When I can say a set is a Lebesgue measurable set, when this property is satisfied. So for all A is subset of R. For any subset A of R, from this figure I can write A is equal to A intersection E complement union A intersection E. A intersection E complement union A intersection E is nothing but my complete A. Okay, so from countable subadditivity, I can write this as outer measure of A is less than or equal to outer measure of A intersection E complement plus outer measure of A intersection E. So to prove m star of A is equal to m star of A intersection E plus m star of A intersection E complement. So what is this? In order to prove one quantity is equal to another quantity, we can write like this. No, one quantity is equal to another quantity. In order to prove this, I can prove m is less than or equal to n and m is greater than or equal to n. From these two, I can say m is equal to n. So here one inequality is proved from countable subadditivity property. So for definition, it is suitable if you say for Lebesgue measurable set definition, it is enough if you say m star of A is equal to m star of A intersection E plus m star of A intersection E complement for all A is subset of R. But for proving it Lebesgue measurable set, it is sufficient to prove that m star of A is greater than or equal to m star of A intersection E plus m star of A intersection E complement, because the reverse direction of inequality will be automatically satisfied by countable subadditivity property. So it's fine if you prove this inequality. Then you can say that m star of A is equal to m star of A intersection E plus m star of A intersection E complement. That implies E is Lebesgue measurable set. So the question is, why the Lebesgue measure is defined in the way it is defined. This is the way we defined Lebesgue measurable set. Why we have to define in this way? Whether we defined Lebesgue measurable set, whether it is in a right path or not. Let us check that once. So I have told you that countable additivity is not true in the case of power set of R. That is m star of union I is equal to 1 to infinity EI is not is equal to I is equal to 1 to infinity m star of EI whenever EI intersection EJ is equal to null. This is not possible in the case of power set of R. So what we have did, this is power set of R, that is m star. We are restricting our study to its subset, that is power set of R's subset. This is subset of R, in which finite additivity is true. Here finite additivity is true. So this is our Lebesgue measurable set now. I have told you that m star is for m star, finite additivity is also not true. That is, in case of power set of R, we cannot define finite additivity property also. So it means that if I consider any two set A and B such that A intersection B is equal to null and m star of A union B will be less than or equal to m star of A plus m star of B. This type of set you can find. That is, in the case of A and B are pure subsets of R. Now let us consider two Lebesgue measurable sets. So if E and F are Lebesgue measurable set, then I have to check that m star of E union F is equal to m star of E plus m star of F. This is nothing but finite additive property. So I am defining E and F for Lebesgue measurable sets. Okay. So I can write m star of E union F is equal to m star of E union F intersection E plus m star of E union F intersection E complement, using the definition of Lebesgue measurable sets. So E and F are disjoint sets. This is E, this is F. So what I will get if E union F intersection E means E union F intersection is E itself. So similarly for E union F intersection E complement. So E union F means whole thing will come, this whole thing. Intersection E complement means it will be F. So I will get m star of E union F is equal to m star of E plus m star of F. So this means that I have achieved finite additivity. Finite additivity. So you can see that we have achieved finite additivity. It means that by defining Lebesgue measurable set in the way we have defined, we have achieved at least something. Okay. So this tells us that we are in the right path. Now I have proved for finite additivity. Then we can slowly move to the countable additivity also. So this says that we are in the right path. That is the way we have defined Lebesgue measurable set is there. No, that is correct. So now let's move to the properties of Lebesgue measurable sets. The first property says that a set E is Lebesgue measurable set if and only if its complement, that is E complement, is Lebesgue measurable set. That means if I consider this box as Lebesgue measurable set, if E sits inside this box, then EC also sits here. This is what I supposed to prove. So let us consider E is Lebesgue measurable set. From definition, this is possible if and only if m star of A is equal to m star of A intersection E plus m star of A intersection E complement. This is from definition of Lebesgue measurable set. So if and only if m star of A is equal to, I can write E as E complement whole complement. So m star of A intersection E complement whole complement plus m star of A intersection E complement. From summation, since summation is additive, I can replace these two. So m star of A intersection E complement plus m star of A intersection E complement whole complement. This is equal to m star of A if and only if. So from this I can say that this is possible if and only if EC is Lebesgue measurable set. So when EC is Lebesgue measurable set, then from our definition I can say that m star of A is equal to m star of A intersection EC plus m star of A intersection E complement whole complement. The next property is both phi and R, real line R, or Lebesgue measurable set. So in order to prove this, I will start with R, proving R is Lebesgue measurable set. To prove R is Lebesgue measurable set. So let's start like this. A be any subset of R. If A be any subset of R, I can write A is equal to A intersection R using set theory property. So this implies m star of A is equal to m star of A intersection R. Okay. So m star of A is equal to, I will add 0 to this since that makes no difference, plus 0. We know that outer measure of an empty set is 0. So I can write this 0 as outer measure of null because